Good day everyone! We are happy to present our investigatory project titled Discovering, Proving, and Generalizing Algebraic Rules for 29, 47, and 53 using modular arithmetic and ICT tools. I am Princess Mancilla and together with my partner, Princess David. Together, we will walk you through what our study is about, how we did it, and what we found. To start, let us go over with the introduction of our study. This part will cover the background, our research question, and also our objectives. Most of us already know simple tricks to check if a number can be divided evenly by another number. For example, a number is divisible by 2 if it ends in an even digit, by 5 if it ends in 0, by 3 or 9 if the sum of its digit can be divided by 3 or 9, and by 11 if you get a certain pattern when you add and subtract its digit 1 by 1. But here's the problem. There are no simple commonly taught rules for prime numbers like 29, 47, and 53. So, in the study, we wanted to create simple divisibility rules for these three prime numbers. We used a branch of math called modular arithmetic to build these rules. We proved that the rules really work, and we tested them using computer tools to make sure that they are accurate. Our main research question is this: how can we create divisibility rules for the prime numbers 29, 47, and 53 using a method called linear congruences? We also wanted to prove that these rules work for any positive whole number, test them using computer tools, and also combine everything into one general method that can work for any prime number and that does not divide 10 evenly. Our general objective is simple. We want to create, prove, and test divisibility rules for 29, 47, and 53. On top of that, we want to combine these three rules into one general method that can be used to build a divisibility rule for any prime number that does not divide 10. And also, we have 6 specific objectives. First is to find what we call the multiplicative inverse of 10 for each of the numbers 29, 47, and 53 using a method called the Euclidean algorithm. Second is to build a digit-based divisibility rule for each of the 3 prime numbers, choosing whether to add or subtract based on which method uses the smaller multiplier. Third, to prove that each rule we created is mathematically correct and will work for any positive whole number, not just a few examples. Fourth, to test how accurate our 3 rules are by using spreadsheet tools like Excel or Google Sheets on a large set of numbers. Fifth is to combine our 3 findings into one general rule and procedure that can work for any prime numbers that is co-prime to 10, meaning it does not share a common factor with 10. We also turn this into a reusable digital tool. And last, to compare our new divisibility rules with the classic Vedic method called the oscillator method, and to talk about how our rules can help in teaching math. Before we go deeper into our procedure, let us first explain some important math concepts we use in this study so everything will be easier to follow. The first concept is divisibility. This simply means checking if one number could be divided by another number with no remainder left over. Second is modular arithmetic. This is a way of doing math using only the remainder after dividing. It helps make big number problems simpler. And third is the congruence. 2 numbers are called congruent under a certain number if they leave the same remainder when divided by that number. Fourth is the multiplicative inverse. This is a special number that when multiplied with another number gives a result that is congruent to 1. This is the key tool we use to turn a hard divisibility problem into a simple rule. Now, let us talk about how we actually carried out the investigation, from the tools we used down to the step-by-step procedure. Let us start with 29. The first thing we needed was the multiplicative inverse of 10 under modulo 29. Using the Euclidean algorithm, we found that this number is 3 because 10 times 3 is equals to 30 and 30 leaves a remainder of 1 when it is divided by 29. Since 3 is a small, manageable number, we use the addition method to build our rule. Take the last digit of the number, multiply it by 3, then add the result to the remaining digits. Keep repeating this process until you get a small enough number. If that final number can be divided evenly by 29, then the original number is also divisible by 29. We also proved this rule works for any positive whole number using modular arithmetic, and we tested it using our spreadsheet tool to make sure it gives the correct answer every time. Next is 47. We again used the Euclidean algorithm to find the multiplicative inverse of 10 under modulo 47. This time we found that using subtraction gives us a smaller and simpler multiplier, which is 14. Because 10 times 14 leaves a remainder that is congruent to negative 1 under modulo 47. Because the subtraction method gives the smaller multiplier here, we use it to build our rule for 47. The rule is, take the last digit, multiply it by 14, then subtract the result from the remaining digits. We keep repeating this until we reach a small number. If that final number can be divided evenly by 47, then the original number is also divisible by 47. To show that our rule really works, we tried it on 2 examples. For our first verification example, let n be equals to 611. So a is 61 and b is 1. Following our rule, 14 times 1 minus 61 is equals to negative 47. Since negative 47 can be divided evenly by 47, this tells us that 611 is indeed divisible by 47. And it really is, because 611 is equals to 47 times 13. And for our second verification example, let n be equal to 612. So a is still 61 and b is now 2. Following the same rule, 14 times 2 minus 61 is equals to negative 33. Since negative 33 cannot be divided evenly by 47, this tells us that 612 is not divisible by 47, which is correct. These 2 examples shows that our rule gives the right answer both when a number is divisible by 47 and when it is not. Now, for our third prime number, which is 53, using the same Euclidean algorithm process, we found that the multiplicative inverse of 10 under modulo 53 is 16. Since 10 times 16 leaves a remainder of 1 when divided by 53, 16 turned out to be the smaller multiplier, so we use the addition method again. Here is the rule for 53. Take the last digit, multiply it by 16, and add that result to the remaining digits. Repeat this process until the number becomes small enough to check. If it can be divided evenly by 53, then the whole original number is divisible by 53 too. We proved this mathematically and confirmed it works correctly using our spreadsheet and our divisibility rule visualizer tool. Since we are done, let us proceed to part D, where we combine all 3 results into one general rule and procedure that can be used to create a divisibility rule for any prime number that does not divide 10. And also in part E, where we verified all our divisibility rules using computer tools to confirm that they were correct.
Good day everyone. Now for the next slide, we have part D, a general theorem for any prime not dividing to 10. So after dividing, separate divisibility rules for 29, 47, and 53, we notice that they all follow the same mathematical pattern. So instead of treating them as three different techniques, we combine them into one general theorem. So this is the part D. So the theorem applies to any prime number except 2 and 5 because only those primes divide 10. So for every other prime, 10 always has a multiplicative inverse modulo that prime. So we call this inverse the magic multiplier, denoted by M. Once this multiplier is found, it can be reused for every divisibility test involving that prime. So we first write any number in that form. N is equals to 10a plus b, where b is the last digit and a is the remaining digit. So if the multiplier m is relatively small, meaning it is less than or equal to 1/2 of the prime, so we use the addition rule a plus m times b. So however, if the multiplier is large, we instead use its complement, p minus m, which gives us the subtraction rule m prime times b minus a. So in other words, every prime has one simplest multiplier, and that determines whether we use addition or subtraction. So this is our next slide. We have here the formal proof. So to formally prove the theorem, we begin by letting p be any prime number other than 2 or 5. So since p and 10 are relatively prime, the extended Euclidean algorithm guarantees that 10 has a unique multiplicative inverse modulo p. So we denote this inverse by m, which satisfies the congruence. 10m is congruent to 1 modulo p. So this is the key property that makes the entire divisibility rule possible. So next slide for our proof. So next we express any positive integer as n is equals to 10a plus b. So if n is divisible by p, then 10a plus b is congruent to 0 modulo p. So since multiplying by the inverse does not change congruence, we multiply both sides by m. So this transforms the expression into a plus m times b congruent to 0 modulo p. So therefore, n is divisible by p if and only if a plus m times b is divisible by p. So this proves the addition version of the theorem. Now, suppose the inverse m is large. So instead of using it directly, we define another value. So we have m prime is equals to p minus m. So this is gonna enter tong subtraction. So since m prime is smaller, it makes the mental arithmetic much easier because m prime is congruent to negative m modulo p. That's why we can write this as the congruence into the equivalent subtraction form. So m prime times b minus a is congruent to 0 modulo p. Therefore, checking whether m prime times b minus a is divisible by p gives exactly the same answer. Next is, the important point is that both the addition and subtraction rule come from the same mathematical proof. So the only difference is whether the inverse or its complement is the smaller multiplier. Therefore, this theorem works not only for 29, 47, and 53, but for every prime number that does not divide to 10. So this shows that our earlier divisibility rules were not isolated tricks, but special cases of one general mathematical principle. Next slides, we have our part E, which is the computational verification using ICT tools. So after proving the theorem algebraically, we verified it using ICT tools. So we created spreadsheet formulas that automatically separate each number into A and B, repeatedly applied the divisibility rule, and compared the result with the spreadsheet built-in modulo function. So this can be seen at the appendices, and we have separate file for the spreadsheet. So this allows us to quickly test hundreds of numbers while eliminating possible human computation error. So we have ICT verification for large data. To strengthen the reliability of our theorem, we expanded the test beyond a few examples. For each prime number, we tested 400 carefully selected integers, so including both multiples and non-multiples. So we also perform a much larger verification by testing every integer from 1 up to 199,999. So in addition, we develop a general spreadsheet tool that automatically computes the correct multiplier for any valid prime and applies the theorem directly. Another ICT verification is GeoGebra. This is just an recommendation. So aside from spreadsheet, we also use GeoGebra or CASView and can be accessible online. So GeoGebra allows us to verify the modular congruence, symbolically and visually demonstrate how repeated application of the rule gradually reduce a large number into a much smaller one. So this computational verification complements our mathematical proof because it demonstrates that the theorem works consistently in actual computation. And then for our results, we have here the table 1. The first table summarizes the spreadsheet verification. So for each prime, 29, 47, and 53, we tested 400 integers consisting of both multiples and nearby non-multiples. So every single test matched the result produced by the mode function. So this means that all three divisibility rules achieve 100% accuracy with zero mismatches. So for the table 2 and 3, we have here the second table presents the large scale verification. So instead of only 400 numbers, we tested every integer from 1 to 199,999 for each prime. Again, there were zero mismatches, showing perfect agreement between our divisibility rules and the standard modular computation. So the third table demonstrates the general theorem by manually applying it to one sample number for each prime. So in every case, the theorem correctly predicted whether the number was divisible or not. And now let's move for analysis and discussion. So these results strongly support both our algebraic proof and computational verification. So one interesting observation is that some rules use addition while others use subtraction. So this is determined by whether the inverse of 10 or its complement is smaller multiple. So another observation is that repeated application of the rule reduces the size of the number very quickly. So in fact, during our large scale testing, no number required more than 3 iterations before becoming small enough for easy verification. So most importantly, the result answer our research question by showing that one general theorem can successfully generate divisibility rules for any prime that does not divide 10. So, in conclusion, this investigation successfully developed divisibility rules for the prime numbers 29, 47, 53 using modular arithmetic and multiplicative inverse. So each rule was mathematically proven through formal congruence proof and computationally verified with perfect accuracy. So more importantly, we established a single general theorem capable of generating divisibility rule for those prime numbers, and this divisibility rule for any prime number other than 2 and 5. So therefore, the study achieved all of its objectives and demonstrate how modular arithmetic mathematically proof and ICT tools can be combined to create a simple, reliable, and reusable method for testing divisibility. So for our reflection, conducting this mathematics investigation is more than just deriving divisibility rules. It also strengthening our understanding about modular arithmetic, congruences, and mathematical proof. So one of the greatest challenges that we'd encounter in deriving the rule for prime number 47, unlike 29 and 53, where the addition form naturally produces a small multiplier. So the inverse for 47 resulted in a relatively large value. So this made the computation less practical. So through further analysis, we realized that using the complement of the inverse produce a much smaller multiplier, leading to the subtraction form. So this experience taught us that different looking divisibility rules can actually be explained by one underlying mathematical principle. So another valuable lesson was seeing how theoretical mathematics and technology complement each other, while the formal proof established that the theorem is always true. So that's what we used earlier, and then also relevant for high school teaching, because it gives a new way of finding its divisibility by having a general form or general theorem of finding such primes like 29, 47, and 53. So for recommendation, we have, based on the findings of this investigation, we recommend several directions for future research. So first, the general theorem may be applied to other two-digit prime numbers such as 61, 67, 71, and beyond to develop a complete collection of divisibility rules. Second, also, further researcher may investigate whether using the last two digits instead of only the last digit could produce even simpler divisibility rule for larger prime numbers. Third, although spreadsheets successfully verified our results, programming languages such as Python could be used to test much larger data sets more efficiently. And finally, we recommend exploring the application of this theorem in mathematics classroom as an enrichment activity. So, since the investigation combines number theory, proof, and technology, it can help students develop deeper conceptual understanding instead of simply memorizing the divisibility rule. So, here's our references. We use several books, studies about supporting the discussion of our mathematical mathematic investigation project. So that concludes our mathematics investigation project entitled Discovering, Proving, and Generalizing Algebraic Divisibility Rule for 29, 47, and 53 using modular arithmetic and ICT tools. That would be all. Thank you and God bless us all.